We are happy to have Shah who will tell us about Extremal Lagrangian Tori in Toric domains.
All right. Thank you very much for the invitation. So this talk has two parts. First, I will review a variant of a Gromov-Witten invariance that counts holomorphic curves satisfying a geometric constraint, which I call a local tangency constraint. And then I will explain some applications to a special kind of Lagrangian embedding that I call extremal Lagrangian embeddings into toric domains. So this is based on my PhD thesis in Berlin. Right. So the local tangency constraint introduced by Cieliebak and Mohnke is defined as follows. So you take a symplectic manifold M and pick a point P, and I choose a compatible almost complex structure that is integrable near the point P. And then I choose a real codimension 2 complex submanifold D that contains the point P. This D, I just choose a germ of such a submanifold. So it's something that could contain in the neighborhood of P. And now consider a holomorphic sphere that passes through the point P. So there's a point on the sphere Z that is mapped to P. Next, I choose a holomorphic function G that is defined near P, and that realizes this divisor as a regular hypersurface. Okay. And then I choose holomorphic coordinates F around the point Z in the domain. If you compose these maps, you will get a holomorphic function from C to CR, so that map the point Z to 0 to 0, right? Now, the holomorphic sphere U is said to be tangent of order k-1 with respect to the divisor D if the first k-1 derivative of this map vanishes at 0. Okay. And if this happens, then I call K the contact order of the map U to D. There is a geometric interpretation of this contact order. If you take a smooth perturbation of the holomorphic curve U near the divisor D to make it transverse to the divisor, then the sign count of transverse intersection to D will be equal to this number K. Okay. So for instance, if you take K equals 2, then this tangency just means that the map U maps the tangent space of the sphere to this codimension 2 subspace of the divisor. Next, I consider the moduli space of holomorphic sphere with this constraint. So you pick a homology class A and positive integer of K, and consider the moduli space of somewhere injective curves in the homology class A. And you quotient it out by the automorphism group of CP1. Okay. Now these moduli spaces are generically regular. So for generic omega almost complex structure, the moduli space is regular and oriented, and the dimension of this is given by this number. So what is this number? If I don't have any constraint on the moduli space, then this will be the dimension of the moduli space. Now I add a mark point that increase the dimension by 2, but then I ask that mark point to pass through this fixed point P, which reduce the dimension by 2n. And then there is this constraint on the derivative that reduces the index by this. And it gives, I mean, to interpret this, this number, you take the jet evaluation map from the unconstrained moduli space to the k-1 jet bundle, and the jet bundle of the divisor D will be of codimension 2 k-1, and so the evaluation map is transposed generically, and it reduces the dimension by 2 k-1. That's the number. And if you take two regular harmless complex structure, then you can find a generic path connecting them such that the corresponding moduli, parametric moduli space would be an oriented smooth cobordism. All right. So for reference, the reference for this is this paper of Cieliebak, Mohnke, 2007. So these moduli spaces leads to a definition of homogeneous type invariance. So for generic J, this moduli space is rigid and it's smooth, and one can count with the sign count of element, then that's an invariant. So it doesn't depend upon the choice of the constraint, the divisor, and the almost complex structure. Okay. Next, they made a computation. So for if you take M to be CPN and take it to be the homology classable complex line, then this count equals n-1 pictorial. And the idea behind this computation is that in degree 1, holomorphic spheres or maps are given by homogeneous linear polynomials, and the k-1 constraint gives you n-1 algebraic equations and the coefficient of these polynomials, and then Bezos theorem tells you how many solutions you should have, and in this case, it's n-1 pictorial. To prove theorems like this, one has to understand like the Gromov compactness of these moduli spaces. And in this case, it's important to understand what happens to the tangency constraint as a smooth curve degenerates to a nodal configuration. So the following lemma describe this situation. Take a sequence of holomorphic spheres that satisfy the constraint k-1, and let's say it degenerates to some nodal configuration. Now there are two possibilities. First one is that the constraint mark point is inherited by some smooth component which is non-constant. Then since on smooth non-constant components, the Gromov convergence is C infinity convergence, so therefore this constraint will be preserved. But it is possible that the constraint mark point is inherited by some constant component in the nodal configuration, so it can goes to a ghost. And so let's say this is the case, and the nodal configuration is I have drawn here. I mean, it's not a stable map, but just to explain the statement of the theorem. Let's say the constraint mark points goes to the ghost here. And then you consider the maximal subtree represented by the constant components attached to the ghost. And you look to non-constant components that are attached to this maximal tree. So in this picture, U1, U2, these are the non-constant maps components. And they have nodes with these ghosts. So let's say the nodes are realized by the points Z1, Z2, and so on. Now, in principle, these points are mapped to the point P where we have placed our divisor D. So they will have some tangency to that divisor, and if you add up, then the lemma says that it should have add up to what we started with. So basically, you don't lose the constraint, but it just gets distributed over the non-constant components. So the possible stable maps that can appear in the compactness of your moduli space are the ones where the constraint mark point goes to a constant component, but the adjacent non-constant component satisfy a tangency constraint that adds up to what you started with, or those stable maps where the constraint mark point goes to a smooth non-constant component. In both cases, if your manifold is monotone, then the freedom index of this configuration is at least 2 less than the freedom index of the sequence that degenerate. And so generically, this kind of configuration lies in codimension 2 strata. And so if your moduli space is already rigid, then for generically, this kind of configuration would not appear. And that's what the theorem claims, that a generic almost complex structure, the rigid moduli space is compact. Right. Okay. So next we move to the second part of the talk. So to fix notations, let's start with some definitions. So consider a domain in the positive power of Rn, so something shown in the picture. And then consider the standard moment map given by this. A toric domain is any subset that can be written as an inverse image of some domain. And a toric domain is convex if the reflection of this domain along the x-axis is something that is convex. Okay. There is a number we assign to convex toric domain in general. So the maximal positive number such that you can place this diagonal vector in the omega is called the diagonal of the toric domain, and it's something that is proportional to this line, this diagonal line. So some examples that will appear in this talk are the following. If you take the domain omega to be a triangle with side A1 and A2, then corresponding toric domain is an ellipsoid. And the diagonal for this ellipsoid one can compute to be this number. Okay. And for the ball, where both the sides have equal lengths, the diagonal equals the capacity of the ball divided by 2. And in higher dimension, if you take a simplex, then you have this higher dimensional ellipsoid, and the diagonal of the ellipsoid is this number now. And for the ball, the diagonal equals the capacity of the ball divided by n. Okay. A non-convex toric domain that will appear in this talk, we consider some positive delta, and consider the union of these two strip, vertical and horizontal, up with delta. And the corresponding toric domain is called the non-disjoint union of cylinder, and they exactly intersect along the cube here. Okay. Right. Next, I defined the symplectic area of Lagrangian. Take a smooth manifold L, which I assume to be a torus, but it could be anything. Then the symplectic area we define, so you look to smooth disk in M with boundary on L. And then you consider only those which has positive symplectic areas, and then you take infimum over that number, and that's some number could be 0 plus infinity. Well, if you have no such disk, then it's plus infinity. Okay. For instance, if you take the product torus in Rn, the standard vector space, the symplectic form exact, so any smooth disk with boundary on L will have symplectic area equal to the integral combination of the areas of the component circles. And if you take to be the Klepper torus, then you get this number. And if you take one of the circle component to be irrational, then this integral combination is dense. So therefore, that torus will have 0 symplectic area. Okay. Using this Cieliebak and Mohnke define capacity for symplectic manifold, and it's defined as the maximal symplectic area per Lagrangian torus in the symplectic manifold. So you look to Lagrangian tori, and then you maximize your the symplectic area Lagrangian tori, and it gives you a number which is either 0 or plus infinity. Okay. A Lagrangian torus is called extremal if its symplectic area is maximal, so it equals the Lagrangian capacity. One can ask whether a given symplectic manifold contains an extremal torus. It's not very clear to me. For example, if you take CP1, then this is the Lagrangian capacity of CP1 is 1/2 of the area of CP1, and the equator is an extremal torus. But if you take a closed-oriented surface of genus 1 or higher, then the Lagrangian capacity equals the area, but they contain no extremal tori. And for example, in genus 1, like in torus, if you see it as a rectangle with different side identified, then you can take a loop that covers the whole. So you take a loop of a sequence of loops that converges to the boundary. And that's a sequence that maximizes symplectic area, but it converges to something non-smooth. So there are no extremal tori. And the same argument works. And as you'll see that all convex domains contains extremal tori. So the right condition which ensure the existence of extremal tori is not clear to me. Okay. So there are, in this picture, there are two extremes. So manifold with Lagrangian capacity 0 and with Lagrangian capacity plus infinity. For the plus infinity, one can take the standard Euclidean space, and you take the Klepper tori with increasing radii, and then you get. But for the 0 capacity, I gave an example. You consider this is the Tenza-Pulitov of CP2, and this S infinity is the line at infinity. You take a small irrational ball and you blow it up. It creates an exceptional sphere, and since the capacity of the ball you blew was irrational, the area of this exceptional sphere would be an irrational number. And the rank of the second homology group of this blew up is 2, which is generated by En S infinity. And now if you take any Lagrangian torus in this picture and you consider its symplectic area class, then E is an irrational generator in this picture. So if you take the n primum or the positive area of this class, it would be 0. So any Lagrangian torus in this manifold would have 0 symplectic area, and therefore the Lagrangian capacity is 0. So there are other examples for which the computation is known. So Cieliebak Mohnke computed per CPN. Here I scaled the Fubini-Studi form so that it integrates over lines to 1. Okay, and for the ball it's 1 over n, and in particular it's not a normalized capacity, because for the ball it's 1 over n. Okay. Cieliebak and Mohnke put 3 conjectures about extremal tori in their paper. The first one is that in the unit ball, every extremal Lagrangian torus completely lies on the boundary. And to praise it, using the previous theorem, then it means that every Lagrangian torus of symplectic area when you are in is completely contained in the boundary. Okay. For instance, this picture is not allowed, so it cannot be in the interior. This one, it touches the boundary, but also the interior. And the only possibility that is allowed is this, where you have the hole. In this picture, if you take a Lagrangian torus that intersect the boundary along a half circle, like the fiber of a half vibration, and you take any Hamiltonian isotopy, a global one, that keeps the Lagrangian in the ball, then such a Hamiltonian isotopy will not push such Lagrangian into the interior. This is a classical no-go theorem, I think. Right. The second conjecture is that extremal tori in the standard n-dimensional ellipsoid has symplectic area equal to the diagonal of the ellipsoid. Okay. And the third one is that extremal tori offer a replacement for monotone tori. So in CPN, extremal tori are precisely monotone. Okay. Next, I summarize the progress we have made so far. So Yogis Dimitru Rachel, he proved that in the four-dimensional unit ball, all extremal tori are on the boundary. And there is a unique one up to Hamiltonian isotopy, which is the Clipper torus. So any extremal torus on the boundary of the ball is Hamiltonian isotopic to the Clipper torus, which is extremal. In the proof, he used four-dimensional holomorphic curve techniques, for example, the positivity of intersection and automatic transversality, and therefore this argument cannot be generalized to higher dimension. Miguel Pereira, was a PhD student of Guy Cieliebak, proved in his PhD thesis that the second conjecture is true. So for the four-dimensional ellipsoid, you have the Lagrangian capacity equals the diagonal. And in higher dimension, if there exists a suitable perturbative scheme to define the curve counts for the linear contact homology, then the conjecture is true. The third conjecture actually is true only per CP2. It's known to be true per CP2, not only. So different people in the last 10 years have done some work, and if you put that work together, it gives a proof of this. So in CP2, extremal tori are precisely mono. So in my PhD thesis, I proved that for all and every extremal Lagrangian torus in the unit ball lies on the boundary. Okay. And there are some observations one can make based on this result. Hamiltonian isotopic classes of extremal tori in the unit ball is in one-one correspondence with the Hamiltonian isotopic classes of extremal tori So if any extremal torus in the ball is on the boundary, and then it under symplectic reduction, it goes to CPN -1. And this establish a 1-1 correspondence. Now, since in the CP2 monotone tori are the same as extremal, therefore there's a 1-1 correspondence between monotone tori in CP2 and extremal tori in the 6-dimensional ball. Now, there are infinitely many Hamiltonian isotropic classes of monotone tori in CP2, the Vienna tori, and so if you lift them to the ball, it creates infinitely many Hamiltonian isotropic classes of extremal tori in the ball. So in particular, the uniqueness theorem of Russell doesn't hold if you choose the ball to be of dimension at least 6. Okay. There is a theorem by Biran and Cornia, which says that which computes basically the Romo width of CPN, the complement of a Lagrangian in CPN. So if you take a monotone Lagrangian torus in CPN, then every symplectically embedded ball of capacity n divided by n+1 intersect that torus. So if you take a ball of this capacity in CPN, then any monotone Lagrangian torus will intersect that. Now, here is a small improvement of this theorem. If you have a ball of capacity n divided by n+1 and a monotone torus intersect that ball only at the boundary, then the whole torus would be contained in the boundary of that ball. Okay. So this one is an open ball of capacity, so bit intersect and then should. Now this one I stated only for tori, but at least this hold for Lagrangians that admits metric of non-positive sectional curvatures. Okay.
I think there is some question in the chat.
Mm-hmm. Yeah.
It was from a few slides ago, I think, or maybe two slides ago.
When looked to CN, no, I don't know, because there the Hamiltonian isotope is global one. So there, I mean, if the Hamiltonian isotope don't make the Lagrangians exit the ball, then no. But if you allow that, then maybe. That I don't know.
I see.
Yeah. All right. Now I explain the proof of the main result, which says that extremal tori in the unit ball are on the boundary. Take a Lagrangian torus that is extremal but is not contained entirely in the boundary, and I explained that it leads to a contradiction. So I pick a point on the Lagrangian, but in the interior of the ball. Okay. And next, I extend the ball by some gap delta. And then I compactify to CPN. Of course, I have to scale the symplectic form on CPN. And now I can see L as a Lagrangian torus in CPN. And this allows me to apply the stretching argument of Cieliebak-Mohnke to L. So I pick a metric on L and scale it and then embed its unit coordinates bundle in the Weinstein neighborhood of L. Okay. So this red part, this red neighborhood is the Weinstein neighborhood. Then I consider a point on the Lagrangian, which I still call P, but you can choose it to be different point. And I consider a holomorphic sphere of degree 1 passing through that point with the tangency constraint n-1. And this kind of sphere exists for generic almost complex structure that I explained in the first part of the lecture, the first part of the lecture. Now you apply next stretching to the sphere along the boundary of the Weinstein neighborhood. Then it will create a holomorphic building. The holomorphic building has different levels. The bottom level is the cotangent bundle of Lagrangian. The top level is CPN minus the unit disk, then completion, but that's symplectomorphic to CPN minus L. So I just write that way. And there would be some intermediate levels of the building, which are the symplectization of the boundary of unit disk bundle. Now, analyzing the building shows that in this case, there are only two levels of this building. The bottom one consists of a single smooth punctured sphere with n+1 positive punctures. And it inherits the tangency constraint from the curve we stretched. And corresponding to this, there are n+1 holomorphic planes asymptotic to orbits on the boundary of the Weinstein neighborhood, which is unit disk bundle. And all these planes are basically somewhere injective and they are rigid. Okay, and this one is also somewhere injective. So now if you compactify these planes to disk with boundary on L, you get n+1 disk with boundary on L. Now the intersection number of the holomorphic sphere we stretch with the hypersurface at infinity was +1. So by positivity of intersection in this case, exactly one component in the top level can intersect the hypersurface at infinity. And I say, I denote it by U infinity. And the other component must lie in the complement, which is the unit ball. Okay. So when I compactify these to smooth disk with boundary on L, n disk will be in the unit ball, but this one would be intersecting the hypersurface at infinity. So then the symplectic area of these smooth disks adds up to 1 plus delta, and that's precisely the area of the holomorphic sphere I stretched. And since the Lagrangian is extremal, each of these smooth disks, I mean, they are holomorphic away from the Lagrangian. So they have positive symplectic area. And since L is extremal, each of these smooth disks has symplectic area at least 1 over n. But we have n of them, so it adds up to 1. And so this equation leads to this estimate on the disk that intersect the hypersurface at infinity. The point here is that so when you compactify to these planes to disk, since the almost complex structure is not extending to a smooth almost complex structure on the Lagrangian, So that basically force you these disks to be non-holomorphic near the Lagrangian. So they're just smooth disks. So in the picture, this U infinity is the disk with this area estimate I got. Okay. Now, this is not holomorphic, but for the sake of argument, assume this U infinity is a smooth holomorphic disk with boundary and the Lagrangian that I can deform to some other disk, which I denote by U bar, such that the boundary of that disk passes through the point P. That is the point which I choose in the interior of my original ball, not the extended one, but the original ball. Okay. If I can do this, so the symplectic area would not change because it depends only on the relative homotopy class. And then I take a small neighborhood of the point P, which lies inside the original ball, not the extended. And then I zoom in. If I fix the almost complex structure to be not changing with respect to delta, then I can always pick some positive symplectic area from that neighborhood by the monotonicity theorem. So there is a constant C that doesn't depend on the delta I choose, right? And so it bounds from below the area of that smooth disk. But by construction, I can make the area as small as I want. And this leads to a contradiction.
I'm sorry about the previous slide. Can you say again why you have n before that? Why you have n components or n plus 1 n's?
Right. So first of all, so when you get this building after stretching, so the building cannot generate different components that share a node along the constraint point, because the homology class of the sphere we stretch is the homology class of a line. It's not decomposable.
Okay.
So that means that a smooth sphere would inherit this tangency constraint, and no other component share that a node with this one along the constraint point P. Yeah. So then you look to the smooth components that inherit the tangency constraint n minus 1, and you analyze its index. The positivity of Predom index forces n plus 1 ends.
Okay.
Yes. So, okay, here I'm doing the following thing. So when before stretching,
So it's related to the fact that for a torus, all geodesics have index 0.
So I perturb, so I perturb the flat metric a little bit, such that the geodesics up to some fixed length have Morse index between 0 and n minus 1.
Okay.
Right. And so if I choose that length to be the area of the holomorphic sphere I stretched, then that means that the Reb orbit of these has action strictly less than that number. And so the index of these geodesics would be between 0 to n minus 1. And so the Freedom index, when you write down the positivity of the Freedom index forces this ends to be at least n plus 1. So there could be more than n plus 1, but at least n plus 1 should be there.
There could be more than n plus 1.
Yes, in general, there could be more. But in this case, we must have n plus 1 because of the following argument. So what I do is now take a positive in and consider the holomorphic building going from here. So the component, and so it would be a planar component, right? So, and since there are no contractible geodesics, that planar component intersect the top level, and the top level contains a plane corresponding to that.
Yes.
So topologically, it's a plane, but if you go along the components, it must lead you to a holomorphic plane in the top level because there are no contractible geodesics. Yeah. So now, if you have n+1 ends, you create n+1 planes at least.
Yes.
Now, if you have more than n+1 ends, you create more than n+1 planes. But we know that exactly one of them intersect the hypersurface. So all the others would be in the ball.
Yes.
Yeah. So then I go to this estimate. If I have
okay.
more than one in, more than n, then it leads this guy to have negative area.
Okay. And can you go back again? Sorry to the previous slide. So here you assume that you have n-1 order tangency at point P? Or, okay, so you have P is a very singular point of the curve. Is that what it means? So is it tangent to, what I mean is it tangent to a hypersurface that goes to P?
Yes.
Or is it tangent to P itself?
No, I have placed this codimension 2 submanifold near P.
Okay.
Yes, so the red line is that codimension 2 thing.
Okay.
Yes.
Okay, thanks. Sorry for
that. Thank you. All right. So if I get this smooth disk, then I'm done. So if I can get a holomorphic disk that I can deform to another holomorphic disk such that the boundary passes through this point in the interior, then monotonicity pick up some positive area which is not depending on delta. So that leads to a contradiction. Okay, next I explain how to do that. So I have, right. So consider the positive S1 equivalent symplectic cohomology of the quaternion bundle up to some action C. C is basically the holomorphic, the area of the holomorphic sphere I stretch. You can fix that, but I just keep it. If I take a suitable metric on torus, then I can assume that it's generated by closed geodesics of Morse index between 0 and -1. And I put this grading. The grading is basically n-1 minus the Morse index of the projected Morse closed geodesics. So the Viterbo isomorphism would read like this in this grading. And if I look to the grade 0 symplectic homology, then these are precisely, they're generated by Morse index of, with closed geodesics of Morse index n-1, okay, in this grade. I want to remind that, so in this picture, this curve is rigid, so that forces all the ends to have Morse index n-1. Okay. So next I define a cohomology class in grade 0 as follows. So I pick a Rab orbit, which corresponds to Morse index, closed geodesics of Morse index -1. And I consider holomorphic plane asymptotic to that orbit, which are rigid, okay? And then I take that sign count to be the coefficient and take somewhere those orbits. So it's a finite sum. It resembles something called the Cieliebak element, where it's a there is a class in the contact homology, but it takes care of more general configurations where the curve has multiple negative asymptotics and so on. So this one is much simpler and it's finite, and it's known as the Berman-Sheridan class. But the point is that the planes that I got in the top level of my building, it's basically computing this class. Okay. And for the bottom level, I define these linear maps. So if you take k input orbits, then you assign to it an integer, which is the sign count in a moduli space of puncture holomorphic sphere with k positive in and satisfying a tangency constraint of k minus 2. In particular, if you choose k equals n plus 1, then these linear maps are computing this, and they actually give you augmentation map and the symplectic cohomology with respect to the N-infinity algebra structure. So if I feed the Berman-Sheridan class to these linear maps, it should give me the count of spheres that I stretched, if I, of course, divide by the permutations of the inputs. In particular, it doesn't vanish, which leads to the following lemma, that there exists a generator such that its coefficient in the Berman-Sheridan class, which is given by the sign count of this moduli space, is non-vanishing. So there is a disk in my construction. There is a holomorphic plane that intersects the hypersurface and is asymptotic to some orbit gamma infinity. But when you compactify it to a disk, it gives you smooth disk of that area. Okay. And then I consider that plane with non-vanishing count. And I consider half cylinders where the boundary is mapped to the zero section in the cotangent bundle, but passes through some point P that I choose. And the other end is asymptotic to the orbit of this plane. I mean, this sign count has been computed to be non-vanishing. I mean, this is how I think Viterbo isomorphism is constructed. If you glue these two, you will get a holomorphic disk with boundary and the Lagrangian. And now this holomorphic disk, so if you take the moduli space of this disk, it has a non-vanishing count. So you have the freedom of moving the point P and changing the almost complex structure. And so now I choose my point P to be in the interior of the ball, and then this disk would give some positive area using monotonicity, because I can always choose the almost complex structure to be the standard one in this ball. And this leads to the contraction. Okay. All right. So another natural question one can ask is the following: that if you take a toric domain, which doesn't have a round boundary, but more like some irregular shape, then is every Lagrangian torus in that extremal Lagrangian torus in that toric domain lies on the boundary? So using the previous argument, one can actually prove this for these cylinders, that the Lagrangian capacity of the cylinder equals the Lagrangian capacity of the ball, and every extremal Lagrangian torus is contained in the boundary of the cylinder. And the argument is precisely the same. So in this case, you compactify to Cpn times some big torus, and then you apply the argument above. But one can do better. So in dimension 4, take any toric domain that can be enclosed in some ellipsoid of the same diagonal. So in this picture, this triangle is representing my ellipsoid, and this green line is the boundary of the ellipsoid, and this bluish area is representing the toric domain that has the same diagonal with the ellipsoid. So if I take any extremal torus in this picture, by extremal, I mean that a Lagrangian torus with symplectic area at least the diagonal of the ellipsoid, which is this number. Then it will be contained in the intersection of the boundaries of the toric domain with the ellipsoid. So it can either lie here or here. Actually, all extremal tori will lie in the component of the intersection which contains this Kleppert torus. This is due to the following theorem. Every extremal Lagrangian torus intersect the Kleppert torus that corresponds to the diagonal point. And therefore, it must lie in this component. There are no extremal tori in these kind of components. All of them are staying here. And every extremal torus cannot be displaced. So an extremal Lagrangian torus cannot be displaced from the Kleppert torus using a Hamiltonian isotopy. So that's a non-displaceability. Okay. Next, I want to give an example where the conjecture fails to hold. So I consider this non-disjoint unit of cylinder up width 1/2. Okay. And next, I consider S3, which I think of it as the boundary of the ball up capacity 1. So in this picture, it's this red line. Okay. And I think of it as a half vibration where is CP1. And take an embedded loop L on CP1, which bounds half of the total area of the CP1. So symplectic area is, let's say, 1/2, which is half of the total area of CP1. Now, if you take L to be the equator, then under this vibration, it lifts to the Kleppert torus. That's precisely this black point. But if I take this loop to be something different from the equator, it would lift to something that whose image will just go a little bit above or below. And this is an extremal torus in this non-disjoint union of cylinder that intersect the interior of this non-disjoint union of cylinder. And using this example, one can consider a smooth domain, a star-shaped domain where extremal tori will intersect this interior. Okay. So I quickly describe the strategy for this second theorem. I follow this somewhat similar argument. So I take my Lagrangian L, which intersect the boundary, but also goes to an interior. And then I extend my ellipsoid by some gap epsilon. Now, in this case, I don't have a compactification to CPN, right? Instead of taking compactify to CPN, I consider holomorphic planes that passes through some fixed point that I choose on the Lagrangian, and it's tangent to some order, let's say k-1, and then it's asymptotic to some periodic orbit on the surface of ellipsoid. Suppose I have these kind of holomorphic planes for generic almost complex structure. I can stretch them. And in this case, if you choose these planes of minimal symplectic area, it will lead to this configuration where now I will have a cylinder which has boundary, half cylinder which has boundary on the Lagrangian, but the other one is asymptotic to some orbit on the ellipsoid. And this one has this small area that I can control. Now, in this case, we are in dimension 4, and this is a rigid cylinder. So Wendell's atomic transversality says that it would count positively in its moduli space. So the sign count doesn't vanish, and it's very flexible. We can deform almost complex structure and things. So it will lead to a contradiction in this case. Okay. Of course, this is based on this observation that these holomorphic planes has a non-vanishing count. So here I quote some theorem. So in general, you take a smooth star-shaped domain and a closed Reb orbit on the boundary, and choose an almost complex structure which is SFT type, and consider planes that are holomorphic and asymptotic to the orbit gamma and satisfy this constraint in the interior of the domain. And then you quotient out the automorphism group. Now this moduli space is rigid if the Conic-Zehnder index of the orbit is n-1 plus 2k. Here the index I measure with respect to trivialization that extend to a capping disk for the orbit. Now, I mean, to get some counts from these moduli space, of course, one needs some perturbative schemes to do that, but that becomes very virtual counts. So and it's not clear if they are like counting holomorphic curves, but some more virtual objects. But in dimension 4, things are nice, thanks to the following theorem. If you take X to be a strictly convex non-degenerate toric domain, choose a point in the interior and a local divisor containing P, then for each K, positive integer K, there exists some other integer K bar and a simple elliptic orbit on the boundary such that the following hold. The index of this simple orbit is 2k bar plus 1, and the action is at most the Kate-Gut-Hutchin capacity. And for generic almost complex structure, the sign count of holomorphic planes is asymptotic to EK bar, satisfying this tangency constraint is non-vanishing, and it's positive. And it's well defined, meaning that it doesn't depend on the choices of almost complex structure and the divisor D. And this is a theorem that is not explicitly stated in this paper of Dusan Magdoff and Kyle and Siegel, but it can be recovered from this paper. I think I'm done. Thank you.
Thank you.
Well, I have a question. So assume that you have not a toric domain, but something, some domain which is non-integrable in general. So that you don't have invariant Tori on the Lagrangian Tori on the boundary. And still assume that the optimal torus exists in the kind of closure of the domain.
Yeah.
So then natural question is what would be intersection between such a torus and the boundary? And similar thing was considered in the context of shapes. So, I mean, there is shape by, I don't know, Sikharov or Ashberg, yeah, so of domains. And then, I mean, the question whether this kind of extremal with respect to shape tori, I mean, are contained in the boundary, and if not, and they kind of are attained, so what is the intersection? So the answer is funny. So you get some interesting invariants, sometimes at least interesting invariant sets, which of the dynamics on the boundary, which is the intersection with the torus. And I wonder what's going on here.
It's not clear to me how the intersection would look like. So I haven't, thought about that. So I should.
I see. Maybe it's doable, actually.
I will have a look. Yeah, it's an interesting question. Of course.
Yeah, sorry, I have a question about the divisor intersection. Sorry, there was a question by Dylan.
What about Lagrangians which are not tori?
Sorry, Claude. You can go first. Anyways. Sorry about that. Yeah.
Okay. Oh, yeah. Okay, I can.
A natural question. What about not torus?
Yeah, it's a good question. So the argument will work for any Lagrangian admitting a metric of non-positive scalar curvature, which is extremal. So the area constraint should be there. So if you start with a closed Lagrangian, which has a symplectic area the same as extremal tori, then the argument will work. So they should be contained in the boundary. Up to my understanding, at least. I mean, there's nothing much happening different.
But do they actually exist?
I mean, in R4, maybe no, but I mean, higher dimensions, you can have maybe.
Well, I have one comment about that. I think there are these weird non-orientable Lagrangians in R4. But I think a non-orientable Lagrangian could never live inside of a 3-sphere, because you can't have a non-orientable hypersurface in S3. So something is a bit mysterious, right?
Yes.
So,
But you think you think in high dimension this could happen? That you have manifolds of negative curvature that are extremal? Okay, well,
yeah,
maybe, yeah.
For example, so in dimension 6, maybe if you take S1 times S2, now what is like the maximal, what is the symplectic area of such an embedding? Is it always the case that it's less or equal to 1/3, which is with respect to the Lagrangian? So it's not clear to me if there exists an embedding of S1 times S2 to the unit ball in dimension 6 that has symplectic area strictly less than 1/3.
But S1 times S2 doesn't have a metric of negative sectional curvature.
No, yes, that doesn't have. Yeah, I mean, okay. So, I mean, there are so what you do is you take S2 on the boundary of the ball, which is Legendrian, and you take some number which is not the length of a rep card. And there is an argument by Klaus that you can push this down to create an embedding of S1 cross S2, which is Lagrangian. So there are like embeddings of these.
No, the question I was about to ask, sorry, is about the beginning of your talk. So what you're doing with hypersurfaces, could you do them, I mean, complex hypersurfaces, could you do them with higher codimension objects? I mean, like codimension 2 or...
Maybe can you rephrase, please?
So you say you can find Gromov-Witten invariance by imposing some tangency condition with the complex hypersurface, basically.
Right.
So if instead of a complex hypersurfaces, I wanted something of higher complex of higher dimension in some way. So
All right.
is that possible? Has this been done, or?
It's not considered anywhere that I know, but I think it's doable. For example, so maybe I go back to the theorem. Here, so the moduli spaces will be regular, and yeah, it can lead to, yes, it would. I mean, I don't see any reason why not, but I haven't seen anybody considering them.
Well, the way you're doing it at the beginning with complex coordinates and so on is not so clear in higher dimension, I guess, but I don't know.
Mm-hmm.
Okay, so that's maybe not.
Thanks. Yeah. Maybe Felix wants to ask.
Oh, Shah, thanks a lot for your talk. Can you go back to page 23? I will ask something probably very easy.
23.
Can you comment again about this correspondence between isotopic classes in the closed pool and CPN?
Oh, yeah.
Probably Dylan
This
already
one.
asked, kind of. So what do you exactly say? You say that if you have a torus in the closed pool,
Yeah.
you get one in CPN.
Yeah, so if you have an extremal torus in the closed ball, then the above theorem says it's in the boundary.
Yes.
Yeah. Now the ref, it's so the Reb vector field is tangent to it, so you can quotient it, and then it gives you a Lagrangian torus in CPN minus 1.
Because it's in the boundary.
Yes, and then if you have something downstairs, you can lift it to the boundary of the ball.
Okay. Well,
yeah.
I mean, I think I overlooked extreme. Okay.
Yeah. Okay.
Thank you.
Thanks. Jose, you have a question?
Hi. Yeah, thank you for the talk. I have a very basic question, which is concerning the other conjecture of Cieliebak that you mentioned. Do we know of any example of any convex toric manifold in which extremal Lagrangians are not given by monotone?
You mean something that is different from the diagonal?
Yes.
Okay, in this picture, maybe I should go. All the examples I know, they are monotone. But something that is not monotone. I don't know. I don't think I remember any example of extremal torus that is not monotone. Yeah, maybe this is something going in along with this conjecture of Cieliebak Mohnke that they are, for example, extremals are monotone. So maybe something that you see here. So I don't know any examples.
I guess maybe it's like, can we be more greedy and elevate the conjecture to say that a Lagrangian torus is extremal in any convex toric domain, if and only if it's monotone? Like, is there any hope of that being true, or not?
If you take a if you take a monotone symplectic manifold, closed monotone symplectic manifold. Maybe it's well, it's not clear if every monotone symplectic closed symplectic manifold which is monotone contains a monotone torus. So that's not also clear, right? But one can expect that monotone are precisely extremal tori in general monotone symplectic manifold.
All right. Okay. Thank you.
Yeah.
In the case of closed manifold, is there a connection between extremal and heaviness?
I don't know what the heaviness means, maybe, but there is a connection to this minimality of submanifolds in Riemannian geometry. So I think there is a theorem by Cieliebak and Goldstein, I guess. It says that monotone Lagrangian torus in CPN is monotone if and only if it is minimal with respect to the Venus-2D metric.
I see. Thank you very much.
And so this would say that extremals are the same as minimal.
Okay, thank you.
Okay, so let's thank Shah again.